All right. Lecture number 36. Can you hear in the back? Announcements. There is a recursive art contest, which is completely optional, but I hope some of you participate. You participate by creating anything you want in the Scheme language. There are some limits to how long your program can be, and those are described at the bottom of Project 4. Take a screenshot of whatever comes out when you run your code and email both the screenshot and your code to Albert. There's his email address. If you ever forget it, it's here at the top of the course website as well. Can't wait to see what you've come up with. Homework 9 is due on Wednesday. It's about SQL. It's worth double. Why? Because we skipped homework last week, so this is like a big homework. Get ready to spend some time on this homework. If you need some help, there's a homework party tomorrow from 5 p.m. to 6:30 in 2050 VLSB. And then another great way to get help on this homework is to go to lab this week. We're intentionally making the lab a little bit shorter just to make sure that you have time to finish your homework and ask questions while you're in lab. So that's probably the best possible place to go with questions because the lab assistants are there in addition to your TAs. Any questions about that? There's a question, but I haven't found it. Who has a question? There. Angela says what? Oh, that's a lie. It's out of 4. I apologize for lying to you. I will correct that soon. Thank you. He thought it was worth even more points than 4, but it's not. It's worth 4. Okay, there's also a quiz this week. We'll release it tomorrow sometime. It'll be due on Thursday. That one you have to work on your own. So save some time on either Wednesday or Thursday to finish the quiz. I just want to make sure that you actually know SQL before this course ends, because it always shows up on the final exam. This Friday will be the final day of class. There will be no videos posted beforehand, and that's a ploy to get you to come. There will be lecture, but the last 15 minutes will be reserved for you to fill out a survey. It's an official survey that you'll fill out in every single computer science and electrical engineering course in this university so that we can keep track of how things go over time. So it's really helpful to get your feedback on that. And so I want you to come to lecture. Since you didn't get an extra bonus point on the online lecture, I'll give you a chance to get it in the physical survey. Sorry, not online lecture, but the online survey that I posted before. As a class, you didn't quite meet the threshold I said of 85%. So now I've set a threshold of 60% for this Friday. It's lower because people have to actually physically show up and sit in these chairs in order to fill out the survey. So mention to your friends if you see them that Friday would be a great day to actually come to class. And thank you all for actually coming today. Questions about that? Okay. So what's going on in this course? We're talking about data processing techniques. We learned a declarative language for doing that. And then last Friday, Soumya Basu told you about distributed programming. So this is situations in which you have multiple different computers running multiple different programs and somehow communicating with each other, which happens all the time these days. It's fundamental to the internet, but it's also fundamental to data processing applications. And what we're going to talk about today is why, if you want to process a lot of data, you actually need to worry about multiple computers at the same time and networking and distribution of your data across multiple machines. So almost everything in this course has been a topic that people thought was a good idea for a long time, multiple decades. The topic of today's lecture is a little different, in that it was a technique invented recently, in the 2000s. but it was one that was completely transformative in the way that people built data processing systems. So what we're going to learn about is a framework called MapReduce. Now, it uses ideas that you already know about, but it was a systems framework that was developed in order to run big applications that process lots of data, like all the text on the web. One of its first applications was actually Google Translate. A later application, and one that it's still used for, is to build the index behind Google Search. So it was developed originally at Google, and then the open source community thought it was a good idea to bring it to everybody else. And so now this is something that's used quite broadly throughout industry and research applications in order to handle big data sets. So that's what we'll learn about. Hopefully you'll like it. Before I tell you about that, we do have to cover one old idea that was a really good idea, and that's called the Unix operating system, because the MapReduce framework is built on top of it, so we need to understand some fundamental ideas there. So Unix is what you use when you go onto the lab computers and log in, but it has an important place not only in our current day computing, but also in the history of computing. It was one of the kind of great outputs of computer systems research. So what is systems research? Well, this is a branch of computer science, one of the largest branches of computer science, that deals with how people are going to build applications. So what tools do they use? And what abstractions do they use? And research is the process of trying out different abstractions to see which ones actually make people more productive or more effective. So like all branches of computer science, this branch has many sub-branches. People who work in systems work somewhat in operating systems, so that's one of the large branches. An operating system is an abstraction. It provides a stable, consistent interface to unreliable or inconsistent hardware. So computers don't break as much as they used to, but they still are a faulty system. They don't always do exactly what you expect them to do. Sometimes they try to read something off of a disk and it doesn't work out and they have to try again, and so there's all this complexity and stuff is kind of misfiring all the time or taking longer than it should. And the operating system is there to make you feel like you're using something much more stable than it actually is. Networks are another important abstraction in programming where there's this really complicated process that gets information from one computer to another computer, especially over the internet. And it fails sometimes as well, because there's some problem with the network, that someone turned off a computer somewhere along the way, or you can't get the Wi-Fi signal you want. And the network abstraction is to provide this robust data transfer interface where the programmer who's building the application just has to think about what they want to send, but not the strategy that they're going to use to send it, even if the communications infrastructure that this is actually running over is changing all the time, and people are adding new wires everywhere or taking them away. Another big branch of systems research is databases, and SQL is the user-facing language that interfaces with most databases. And the whole point of a database is to give you this declarative interface where you just write your select statement in order to get whatever you want. And it's up to the database system to figure out how to compute the result of that select statement. So it might try things in different orders, it might skip some steps, it might use some caching, whatever it does that may be very complex, it feels very simple to use because you just write your select statement, it runs, and you get what you want. And distributed systems, which we'll talk about today, provide some unified interface to a whole cluster of machines. So let's say what I want to do requires more than one computer. I don't want to have to think about what each computer is going to do, because there might be thousands of them. Instead, I want to treat them all as one big blob. Like my data center is just my computer. How do I program to tell my whole data center what I want it to do? And that's one of the goals of distributed systems, to provide an abstraction that says, I can command lots of machines at the same time to all communicate together. So if you're thinking about what branch of computer science sounds most interesting to you, you'll see there are courses aligned with several of these different topics, I guess all of them, and so you could decide whether that's something you want to pursue in the future. Okay, so what's similar about all these different things? Well, all effective systems hide complexity behind abstractions, but they don't limit what you can do with your computer. They retain the flexibility that this thing's able to compute anything and quickly, even though it simplifies the process. When someone says I'm a networks researcher, they're talking about how they're going to process the communication. So what's the strategy that I'll use in order to make sure that one computer can communicate with another? Distributed systems are thinking about not only communication, but also the computation and the storage that happens among all the different computers and coordinating all of that together. It's kind of a more broad field that relies on networking as an abstraction in order to figure out how to coordinate lots of machines all trying to get one task done. I think that was the last lecture. Like there's peer-to-peer networking applications and there's client-server ones. I mean, that's the kind of stuff that networking people think about. Okay. So now you have like a broad view of what systems research is. One of the great outputs of that was the Unix operating system, lots of which, by the way, was developed here at Berkeley. The BSD Unix, or the Berkeley Unix operating system, was heavily used in research and was developed here. And so it's an operating system, meaning it's supposed to get computers to behave in a robust way. And one of its big inventions was portability. So it actually was the same operating system regardless of which brand of computer you were running it on, which was a really big deal. So in the early days, people would build software just for a particular piece of hardware. So you couldn't just swap out one piece of computing for another and have it all run. But Unix was a portable operating system. So the basic structure of how everything worked didn't change, even if you ran it on a different machine. I don't think it's the very first, but it was one that was used on many different pieces of hardware extensively. So the idea of having something portable didn't start necessarily with Unix, but the vision was only realized with this operating system. Another thing that it really brought to the world was multitasking. So you could have many different processes running on the same machine instead of just having your computer run one thing at a time. And a third was that it embraced plain text instead of just bits. So bits are ones and zeros. Plain text is something someone could actually read. And that was asserted as a common data format used among different applications. So you could actually read what was coming out of your program without another program interpreting it for you. And the nice thing about having lots of plain text everywhere is that you could build lots of small tools and then compose them together. So this is very similar to how I suggest you should build programs in the future, right? Lots of small functions and compose them together in order to build whatever you want. Well, Unix uses the same philosophy. Here's a quote that I like. We should have some way of coupling together programs like a garden hose. Just screw in another segment when it becomes necessary to massage data in another way. So instead of just building one huge program that does everything, you build lots of specialized pieces, and then you decide how they fit together in order to get what you want. And a process in Unix is very much like a function in Python. There's some input that comes in, but in this case, by default, it's text input. Now, that text could represent anything, and you're not restricted to only using text. But that's the typical way that a process works, is that it takes in some text, out comes some other text that has been transformed in some way by the process. And then if you want to see what's going on while the process is running, there's actually a second output. Now these names, standard input, standard output, and standard error, are particular to the Unix operating system. And they are streams of text. Now, what is this text? How does it behave? These streams, standard input, standard output, and standard error, behave a lot like a Python iterator. You can ask what's next, or you can put stuff into it incrementally, and the process will just process whatever data comes in and send whatever data comes out and describe what's going on to the programmer through this error channel that tells you whether anything's going wrong. Okay, so keep the picture in your mind of a function. Think, oh, a Unix process works kind of like that. Okay, so what's all this business about composing stuff together and modularity? Well, let's do an example. So here are all the PDFs and example files for the entire course in a directory called slides on my computer. You can get all these on the web, too. Now, the program ls doesn't need to take in anything. It just uses the current directory. But it outputs as text all of the different names of files in the current directory. And if I just want to look at them, I just write ls. But if I want to do something with them, I can pipe that output into some other input. So this pipe character is supposed to be the connector between guard and hoses. The ls gives me all the names of the files, and then I pass that as input to some other program that uses that information and massages it in some way. In this case, I'm going to get rid of anything that contains the letters PDF. So now instead of having all the slide PDFs and all the example files, since I've gotten rid of all the PDFs, I'm left with only the example files from the course. Now, what might I want to do with them? Well, let's say I want to know, like, how much of this course is Python versus SQL versus whatever that other language was. Well, I could take each one of the names of the example files and just get the last few letters, everything after the dot. So there's a specialized program called cut that takes in a line of text and splits it up on a dot. So you have to tell it what the dot is. You say the delimiter is a dot, and I want the second thing, meaning the thing after the dot. Okay. So I started with all the names of the example files. Now I've thrown out the numbers. So this used to be 01.py, 02.py, blah, blah, blah. Now it's just pi. Oh, and there's some scheme, and there's some SQL. And one of the lectures had a zip file. That's actually this lecture. Okay. So what? Well, maybe I want to count those. So there's a separate program called sort that takes in whatever input comes in and sorts it. And the nice thing about sorting it is now I have all the pies together, and all the schemes together, and all the SQLs together. If I want to count them, there's another program called unique, which has an option to count how many things there are. So there were 29 different example py files, 4 scheme files, 4 lectures on SQL, and there was this lecture, which has a whole bunch of stuff. Okay, so this is Unix. Lots of little programs. One to list the contents of a directory, one to filter out stuff that has a PDF in it, one to get rid of everything before the dot, one to sort all the results, and one to count them up. And these can be composed together arbitrarily. You just add these pipes, and you're done. Question? Yeah, there are some weird dependencies between these programs. So Unique actually expects that its input will be sorted for it. So you can figure out how to sort it before you pass it into Unique. But it is the case that some of these programs have some expectations about the kinds of things that will come in. I think there's no option in Unique to sort. You just sort first, and then you're Unique. Okay. How we doing? I don't know. Did I lose everyone? Do you have questions? Whoa, someone counted this. and found that there's 38 different files. What's going on there? Well, it turns out that in addition to the regular lectures, there are also extra lectures in this course. Those have been happening on Thursday, and so there's a bunch of stuff that you may not have bothered learning about, like the lambda calculus and Huffman encoding trees, which are counted in these counts. And then there are some lectures that didn't have any examples at all, like the distributed computing lecture last Friday. So that's why the count is not exactly 36. Okay. Okay? Okay. Python programs so the Python language was originally built to do useful things in a Unix environment, meaning running on a computer that was running the Unix operating system. And so there's a very close tie between how Python works and how Unix works. There's a built-in function called input that reads a line from standard input, meaning the standard stream that comes into the application from whatever was piped into it. And the print function, which you're probably used to by now, writes a line to standard output. Okay, so let's write a program. What's my program going to do? Well, forever, it's going to do the following. It's going to print out what you get by joining together all of the different characters in a line of text, separated by spaces. If I run this and I start typing, then it's going to space out my typing. Thanks for the spaces. And then when I'm done, I quit. Oh, it gave me some weird error. Well, that's because I reached the end of standard input. And what happens when you reach this end of standard input and you try to input is that you get an end of file error. So we could get rid of that. We know how. We could just handle the exception. So when it's the case that we reach an EOF error, we'll just do nothing. Pass means do nothing. The reason we need a pass there is that we have to have something in the except clause. Okay, so this version, I can still say, give me some space, bro, and it will add some spaces, but now when I quit, I don't get any weird error message. Now, the cool thing here is that I've built a program that can operate within the Unix environment. So if I list everything that's in the slides folder, and let's say I get rid of everything that's a PDF, and now what I really want to do, instead of counting stuff up, is just space them out, then I'll just run x.py, at which point it will add spaces between all of the different letters in each line of the listing of the directory that I created. So my program can play nicely with all the other programs that are built into the operating system. No, this is just displaying stuff. It's not changing the file name. Whew. That would be a disaster. Yeah, so what's going on here is we're just getting text in and putting text out, and all my program is doing is just manipulating it to put spaces in between. Getting there. Good idea. Getting there. Okay, so this is not the only way to do it. And it was a little bit clunky because I had this try and this except. Well, actually, we can access the standard input and standard output directly in Python using a module called sys. So sys exposes the input and the output as files. So what's a file? Well, you might have some conception of what a file is. It's supposed to represent the contents of some information. It's got a title, etc. Well, really, in Python, a file is an interface that lets you iterate over the lines or write lines to it. So you can add to a file or you can read what's already there. So using these files, which are really just an abstraction for anything that you can read from and write to, you can take advantage of the operating system text processing abstraction to just read what's coming in from standard in and write to standard output. So what do I mean by that? Well, if I import sys, then instead of try while true blah blah blah, I can just say for every line in sys.standardin, which is the file of all of the input, I'm going to print out what I get by joining that line. And instead of printing it, I could also say I want to write to sys.standardout whatever I get by adding a space in between all the letters in the line. So hopefully this will do the same thing. Oh, it does. And as was suggested, I could actually tell Unix that this is a Python program. Now, I know this is going to look cryptic, but just work with me here. So there's some special syntax that you put on the very first line of a file that tells Unix what kind of program this is. At which point, instead of running python3x.py, which still works, I could also just run x.py. And what happens there is that Unix figures out that it's Python. And so we'll run this as a Python program based on what's going on in the first line. Okay, so this is something you have to memorize. There's no magical way for me to describe it to you in 1 minute. It's just part of the operating system is it looks at the first line of the file and says, how can I deduce what this is? And figures out it's Python 3. Cool. So you can build whole programs. All you have to do is write that, and then write this, and you've built a program that you can use interactively with anything else. I can now just run this to space out the letters in some file. Questions? Comments? Yeah, so for any Python file, I could do this, and then instead of running Python 3 whatever, I just type in the file name. Yeah. Okay. So I just told you all about the Unix operating system. You might wonder, why am I calling it Unix when I'm clearly using a Mac? Well, the Mac operating system's current version was built on top of Unix, so it has all that Unix functionality, and then they put some pretty pictures on top. And when you install Git Bash on a Windows machine, you're basically installing a version of a Unix-like operating system there. So this functionality you can get running on basically any computer, including your phone. And the reason you can get it so many places is that people find it so useful that they want to make it run everywhere. Okay, so I told you all that because it's important and everybody should know it, but also because I wanted to describe to you this idea called MapReduce, which, really, just changed the world of distributed programming. It made it so that people who didn't really know much about networking, really didn't know much about how to coordinate different computers, really had never been to a data center, I've never been to a data center, all of a sudden could write distributed applications very easily. And that's all because of clever abstractions. Okay, so really quick, what's big data processing all about? Sometimes you hear this term big data. Big data is supposed to be enough data that if you look at it and analyze it, you could understand something interesting about how the world works. And MapReduce is a framework for batch processing of big data. This is the most buzzwords per sentence I could possibly imagine. But what's going on here is that we're going to learn what MapReduce is. A framework just means something that programmers use in order to be more productive. Batch processing means I have all the data already, and I want an answer about what it's doing, what's going on there. And data is big. Well, people don't agree on what big data is. I mean, how big do you have to be? But a nice rule of thumb is if you can really learn something about the world from your data set, well, that's pretty special. Because for a long time, data sets really didn't tell you about broad, populations and their behavior and what humanity was up to. That just wasn't something that we had data about, but now we do. Okay, so framework is a system used by programmers. I said what batch processing was, and big data is used to describe data sets so large, so comprehensive, that they reveal facts about the whole population, about the whole world. Okay, so the MapReduce idea is that data sets sometimes just get too big to be analyzed by one machine. But if I use multiple machines, then I get multiple headaches because machines break and the communications between them break and some of them run slower and some of them run faster and one of them is running out of disk space, and how do I remember to keep track of all this stuff? Well, those are all the same complications that you get regardless of what analysis you're trying to perform. So MapReduce tries to automate dealing with all the frustrations that would come from running something on 1,000 computers. And how does it do it? It uses pure functions. Pure functions enable an abstraction barrier between what the data processing logic should do and the really hard work of making sure that everything gets coordinated in the right way. So one of my favorite applications built on top of MapReduce is called Google Trends. Did I ever show this to you? I don't think so. Google Trends. You type in some words like dogs and cats, and it tells you, has the world been searching for dogs and cats? If so, how many people search for dogs versus how many people search for cats? Dogs are in blue, cats are in red. You can see dogs are better than cats. You can also see that cats are in steady decline. It's not a good time to be a cat, whereas dogs are just moving up in the world. Now, this is something that is an insight into dogs and cats that nobody was intending to get when they built the Google search engine. It's just part of the data set that you get when you look at what everybody's search queries are. And you can see that some things have, very spiky distributions, like no one knew where Gangnam was, even though it was a real place before it had its own style. But then all of a sudden they did in 2013. Whereas some things are more cyclic, like people search for snow pretty much every year. This is 2006, 2007, 2008, 2009, 2010, 2011, and then there was some snowpocalypse in 2012, which didn't affect us at all, except for apparently some servers in Silicon Valley got warmer dealing with all this traffic. And now people basically don't care about snow. And actually, Gangnam was more important than snow to people ever so briefly, but that didn't last. Okay, so we just learned something about the world. How would we build an application that could do that? Well, you can't keep the history of everybody's Google searches on one machine. There's no such machine that's big enough. So you have to keep little pieces of it on lots of different machines, and then coordinate the computation that reads in all of that, counts up who searched for what when, and then writes it down in a pretty graph like this. And that's one application of MapReduce. Okay, so now we have to learn this abstraction. Here's how it goes. There are 3 phases. One's called the map phase. Mapping, if you remember, in our discussion of scheme and Python iterators, was when you take a function and you apply it to each element in a sequence. So we apply a mapper function to all inputs, and the input can be whatever. It's a line of text, let's say. The output is a bunch of key value pairs, the kind of thing that you'd see in a dictionary. So the mapper takes an iterable value containing the inputs, such as lines of text, and it gives you back 0 or more key value pairs for each input. So here's an example. I wrote this haiku just for this lecture. Google MapReduce is a big data framework for batch processing. Look at all those buzzwords. Okay, what's the mapper do? Well, it's going to take in each line of input and give us back some key value pairs. In this case, the mapper is going to give us the count of each vowel in each line. So there's 2 O's, there's 1 A, there's 1 U, and there's 3 E's in that line. Now we run the mapper, which is just a function, on each line, which means we get the counts of the vowels in the second line and we get the counts of the vowels in the third line. So now we've counted up something about each individual input, but we haven't really figured out how many A's there are in the whole haiku yet. That's the next step. Okay, so there's a second phase in between that I'll talk about later, but the third phase is called the reduce phase, which takes each key, such as O and A and U, and applies a reducer function to accumulate all values associated with that key. Okay, so for the key A, the values are 1, 4, and 1. So the reducer takes an iterable value containing intermediate key value pairs, and all pairs with the same key are going to appear next to each other, so in sorted order. And that means that you can take in all of the different values associated with that key just by walking through the list of key value pairs. And the reducer yields 0 or more values associated with the intermediate key. Okay, so what do I mean? Well, let's keep that in mind. What the reducer is going to do here is take all the counts for the letter A and come up with a sum for the letter A. So it does this by first taking all the key value pairs that appeared here, grouping together all of them so that the A's are next to each other, the E's are next to each other, etc., and then applying a reducer to all the values for A to get 6. And the same reducer applies to all the values for E, in this case to add 1 and 3 and 1 together and get 5. And there are 2 I's and 5 O's and a U. So the mapper phase, the map phase applies a mapper function to each input. The reduce phase applies a reducer function to all the values for each key. And that's all you need to know in order to build a MapReduce application. Question? Is there another I? Oh, it doesn't count capitals. Wait, yeah. That's what I did. I didn't count that capital I. It's too big. Didn't fit in my big data. The question is, how does it verify that you're using pure functions? It doesn't. It assumes you're using pure functions. Now, there are a few checks in the actual implementation that they use at Google to try to detect if somebody did it wrong. And what they do is they just run the same thing twice on occasion, and they check to make sure that the same value came out. But that's not an exact test to see if a function is pure. So it's assuming that you know how to write a pure function, and then uses that in its implementation. Okay. So now we're going to look at some figures from the original paper that was published on MapReduce, so you can see what happens in computer science research. Computer science research is mostly conference papers. They're only 8 pages long, and they have lots of boxes and arrows. This one has some circles as well. And the execution model here, this is the actual figure from the paper that described this in the first place, which is now cited many thousands of times, said that here's what happens. You take the input, you break it up into pieces, you apply the mapper to each piece, you get these intermediate key value pairs, you group them by the key so that all values for the same key are in the same place, meaning all the counts for the letter A are in the same place. Then you apply your reducer to get an output. That's the idea you need to know in order to use it. That's above the abstraction barrier. Now, what's below the abstraction barrier? Well, how a MapReduce application actually executes looks quite different. It says there are actually multiple different tasks, maybe running on multiple different machines. There are map tasks and there are reduce tasks. In a map task, it actually takes a piece of the input and applies the mapper function to each. And then there's this clever idea, which is that you come up with a function that tells you which key is going to go to which reducer task. So the partitioning function you see there can be any function, like just looking at the last digit or something like that, that comes up with a way of sending all the same keys to the same place. And so any key value pair, regardless of which map task it came from, that has K2 as its key, will end up over in reduce task 1, and all the K1 pairs are in reduce task number 2. So this partitioning function is used to make sure that the key value pairs that have the same key all end up in the same machine. That machine is charged with sorting and grouping these things so that all the values for the same key are together, and then applying the reducer function. And what's a task? Well, a task is like a Unix process. It's taking in stuff. It's writing stuff out. And what are these arrows? Well, these are like pipes, except some of these pipes actually run from one machine to another machine over the network. Now, when this paper was originally presented, I wasn't there, but I hear there were like tons of questions. So do you have any questions? It is basically meant for key value pairs. You can write down a lot of computation in terms of manipulating key value pairs. But here, we are thinking about immutable keys, which is a requirement for dictionaries. And in the same way, it's a requirement for this data processing framework, where we're not going to go in and change the values of the keys. Instead, we'll just write down the keys and send them to the right place and then sort them. Okay. So this is called the map phase up here. The shuffle phase, which I never mentioned until this moment, is really built in. It happens, you don't have to say anything. It always happens the same way. It partitions up the key value pairs by key and then sorts them all by key so that they're grouped together in the right way so that the reduce phase can run. So this shuffle phase is built into the framework. It sorts everything for you. Okay, now MapReduce assumes that the mapper is equivalent to applying a deterministic pure function on each input independently. The reducer must apply a deterministic pure function to each sequence of values for the key. Now, why is it this way? Well, you get all the benefits of functional programming, which we've talked about in this course. If you have a bunch of pure functions, a call expression can be evaluated in any order. So if you're summing up a bunch of stuff, you don't have to do it in a particular order. You could have different machines doing different parts. If you're just applying a mapper and it's a pure function, it doesn't matter which input you apply it to first or second. And you get referential transparency. A call expression, like calling the mapper on some input, can be replaced by its value, the result, without changing the program. And since we have these properties, we can get consistent results, even if different machines are running at different speeds. However we partition up the computation. So however we take the input and send some of it to this map task and some of this to that map task, you still get the same answer at the end of the day. And you can even recompute stuff. So why would you do that? Well, something that happens is that it sends some data to some machine and says, please run this mapper function on that. But if it's taking too long, then it'll send the same data somewhere else and say, hey, why don't you give it a try? And if this one finishes first, then it can just ignore that one. Speeds up your whole computation as long as you have enough computers lying around. Okay, let's build a MapReduce application. I'm going to show you what this count vowel thing looks like. Python allows you to write MapReduce applications even if you don't work at Google using an open source distribution called Hadoop. And there's a lab that I won't require this semester, but I can post a link to it. If you want to work through this example yourself, you can absolutely do it. You just write a mapper and a reducer as Python programs. They read from standard input, they write to standard output. So the mapper is supposed to take in each line of the haiku and write out how many times each vowel occurs. So here's the code. It says, for each line, go through all the vowels in A, E, I, O, U, count how many times they show up in the line, and if the count is greater than 0, then emit a key value pair. Now we need a little structure around this. We need to say it's a Python program. We use sys, and we're going to use emit. And what does emit do? Well, it just prints out the key and then the value separated by a tab. So this tells Unix it's Python 3 code. The emit function just writes out a line of text. And then for every line in sys.standardin, we emit all the vowels from line. And that's the whole program. So we can write that program. But since I'm lazy, I wrote it already. Okay, here it is. It counts up the vowels. Where's that haiku I was talking about? Oh, there it is. So if I take the haiku and I pipe it through my count vowels mapper, then what do I get? Well, I get all the vowels in the first line, then all the vowels in the second line, then all the vowels in the third line. If I just run count vowels directly, I can count these vowels, and it will tell me, oh, I spelled it wrong, but it still has the same number of vowels, so we're okay. It'll tell me how many vowels are in each line. Okay, so that was simple enough. I just counted up all the vowels. Any questions about that? Okay, so I wrote that part. I also need a reducer. What the reducer does is it takes in all of the key value pairs after they've been grouped together. It takes an iterator over key value pairs and gives you back all the values for each key. So, okay, I'm going to skip over this because it's kind of boring, but the point is you get the key, like the letter A, and the value iterator, which tells you all the counts from all the different lines of how many A's there were from standard input, and then you just sum up all the values using the built-in Python sum. Okay, so if I take my haiku, I count up all the vowels for each line, and then I sort the result. I get all the A's together, then all the E's, then all the I's, then all the O's, then all the U's, and then I have this little Python program that I wrote called SumReducer, which sums the values for each key. And if I run SumReducer, then it's going to sum up all the counts for A's, E's, I's, O's, and U's, and give me the answer, how many different vowels of each type are there in this haiku. Okay, so that's kind of cool, but we haven't really used the MapReduce framework yet. We've just been using Unix to pipe a bunch of stuff together. But those same programs can be used with the Hadoop implementation of MapReduce in the following way. I just say I start up MapReduce. I say run my count vowels mapper, my SumReducer. Instead of the haiku, I'm going to count all the vowels in all of Shakespeare's plays, and I'm going to put that into a directory called vowels, and then some crazy stuff is going to happen. Okay, so it's giving me a URL. Oh, that's interesting. Let's see what's there. So just by writing that little bit of Python code, I get this website that says, oh, it's working on my job, and it's already completed 100% of the mapping. So it's already counted up all the vowels in each line. And next it's going to do some reducing. Oh, look, now I've refreshed, and there's 73% done. I get this cool graph down here that tells me, oh, it's done a bunch of copying and a bunch of sorting, and it's almost done reducing. If I refresh one more time, it says, oh, I've finished reducing now. Your data's done. It gave me all this text output too, by the way. And when my data is done, then I can look at it just by catting all the vowels, and it says there are 233,000 A's, 387,000 E's, etc., I's, O's, and U's, using just that tiny 2 snippets of code that I wrote, the mapper and the reducer. Powerful stuff. Okay, I'll see you Wednesday.